Welcome to Telescopes 101 with the Mid-Hudson Astronomical Association. This will be an introductory guide to astronomy and telescopes. My name is Steve Dittmar. I'm currently the MHAA President. Before we dive in, I just want to briefly acknowledge a few technical hiccups we ran into with the lecture hall computer system this month. Because of that, the primary recording ended up being a laptop camera, which isn't the ideal angle or quality. I'm also re-recording my narration for the first 5 or 6 slides, since in the initial chaos we forgot to start the Zoom recording right away. Also, at the end of my talk, Jack was streaming some great live footage from our hands-on, in-person Q&A and discussions in the room, but unfortunately Zoom only recorded the stationary audience camera during that time, and so as a result I've cut that final half hour from the recording. We present this Astronomy 101 talk every January, so if you missed it this year or stayed home because of the brutal cold, hopefully we'll see you next year. We'll start with the basic components of a telescope, common types of scopes, different mounts, standard specifications that you'll see in product literature, and some useful accessories. The intention is just to make it easier for you to compare scopes to each other, as well as to use accurate terms when asking questions so you'll get better answers. After the presentation, we normally have time for the hands-on Q&A, but like I said, we had to cut that from the recording. So, telescopes. Every optical telescope has the same goal, which is to redirect a wide swath of light into a small focal point and then magnify and project that image into your eye. Every optical telescope uses a set of common parts to achieve this. Some telescopes use lenses, some use mirrors, and some use both. We'll go over the main types and their differences later, but the design I'll show you here happens to use all the common parts, making it a good one to learn part names on. The blue lines represent a lens or a mirror, and the yellow dashed lines are the path of the light through the scope. So the light enters the telescope first into a large lens or reflecting off a large mirror, which redirects that inbound light. If you have 2 mirrors, the larger one that the light hits first is generally called the primary mirror, and the second, smaller mirror in line would be the secondary. An optical tube assembly, or OTA, holds the lenses and mirrors in the right order and at the precise distances required. The eyepiece magnifies and projects the final focused flat image into your eye. Different eyepieces offer different magnifications and fields of view. The focusing mechanisms help adjust the sharpness to account for slight variations in your optical terrain. The finder scope is a small scope with lesser magnification to help you roughly aim at your target before you look into your eyepiece with a high magnification. The mount is a crucial piece that is ideally rigid and sturdy. The OTA attaches to the mount and the mount articulates to aim the scope at your target. The mount sits on top of the tripod, which is also important to be sturdy so that the image in your eyepiece is not fluttering around with vibrations from nearby traffic or winds, etc. It's also important to make sure that it's strong and wide-stanced enough to support the weight of the mount and the gear on top.
So the finder scope and the main OTA are aligned so that what's in the center of one's in the center of the other. But with the wider field of view on the finder scope, it's easier to center it, to target, and align it. And then when you look into your main scope, you're going to be looking at a higher, more magnified view. So there's also the red dot or reflex finder scope. This is the kind of scope you'd see on like a rifle. Basically, it's a zero magnification kind of alignment. It's still aligned with your main scope, but instead of magnifying what you're actually seeing in the background behind the reticle, which is these illuminated lines, it's just zero magnification behind it. So it's like having a very wide field of view. You don't have to figure out what am I looking at when I look through the scope, through the finder scope versus when I see it with my naked eye. So particularly for larger, brighter things that are naked eye visible, a red dot finder or a reflex scope like this makes it a lot easier, in my opinion, to find it because it's exactly what it looks like when you look through the finder scope as it is when you look with your naked eye. But different people have different appreciations for the different types of scopes. The more magnification you have on your big scope, you might actually need a finder scope with a little magnification because you're looking for smaller, dimmer objects with that larger scope. The one in the top is a very common one called the Telrad. This one here. This is that's a Telrad on top of the scope.
What's the difference between the green and the red?
So some of them you can make alterations to the Telrad that'll give you green or red. I did that to mine. I use the green for when I'm aligning more in the daytime. You need a brighter reticle to see. Red, you normally would use at night. It's not going to affect your night vision as much. So when it's brighter, I tend to switch to the green light. And then when it's dimmer, I'll switch to the red. Not all of them have that option. The default tell red doesn't. Not every one of the rifle finders have that. But the rifle type finder scopes are better built. These are usually solid metal. They usually have a lithium ion battery in them or something. Sometimes this will pop off and you have a standard button cell, but the one I have has a nice magnetic recharger on it. And they're only about 20 something to $50, just like the Telred is. And they're a lot smaller. They work better. I like it on my binocular actually, because there's less room on the binocular to put like a finder on it. And I have a kind of a high power binocular. Anyways, so that's that. So if you go to like the Celestron website and you look at a telescope, you're going to see a technical specs page, and kind of the main ones that are the most interesting that kind of define the capabilities of your scope are going to be the aperture, the focal length, the focal ratio, and then kind of combinations of that come out with what ends up being the highest useful magnification and the limiting stellar magnitude. And also important and sometimes overlooked is the optical tube weight, or any of the weights that are listed on the product. That part is really important just because if you buy something too big, you're not going to use it, right? If we've got a 12-inch Meade scope that was given to us to the club, and it's about 100 and some odd pounds of gear. It's barely liftable for most of the members and not liftable for some of the members. And it's barely something you would want to move it to be a remote scope. So if you get that kind of a scope, you're far less likely to haul it outside when you've only got maybe an hour of good sky to look, or something like that. So pay attention to the weight overall. But the aperture and the focal length and the focal ratio, the aperture is how large the primary mirror or the primary lens is in your scope. And that relates to the light collecting ability of your telescope. So the larger how come all of a sudden we're getting audio? Do you? So the larger the aperture is, the more light you're gathering. So the dimmer object you can see with that scope. And that comes into play with the limiting stellar magnitude that's circled there. The 12.5 is it's inverse relationship with brightness. So as you get larger in that number, you're getting dimmer on the scale. So 12.5 is somewhat dim. Your eye can see down to about, I think it's 6, give or take, if you got good eyes and good skies and dark skies. Exactly. So that kind of gives you a rough idea for, you can see something dimmer. And the larger the aperture is, the dimmer, larger number you're going to see for the limiting magnitude. And that's good to know because you can, in your application that you're using to find targets, your little planetary map on your phone or whatever, you can use that as a way to filter out anything that's dimmer than that, because it won't really be useful to even try and find it. Then you've got the focal length. So the focal length is the distance from the aperture where the light's first hitting your glass or your mirror to the focal point in that scope. And that relates to, it's one of the factors of your magnification, because you take the focal length of your eyepiece, divide that into the focal length of your telescope, and that gives you the magnification of the scope eyepiece combination. The highest useful magnification is really a factor of in most perfect conditions, you might be able to put in the highest useful magnification, meaning you might be able to use, in this case, it's 102 millimeter aperture. You divide into that 240. So what's that? It's like a 2 millimeter. What's that?
Yeah.
No, Tim. Yeah. So you get like a 4 millimeter, or 4 or 5 millimeter eyepiece or something like that. And you're going to end up with like a 200 and some odd X magnification. If you go below that, if you use a smaller eyepiece than that and get a higher magnification than that, you might make the image larger if you're lucky enough that it's actually bright enough to still see it well, but you're not really going to get better resolution on that image. It's just going to blow up a fuzzy image to be a larger fuzzy image. And so the size of the aperture also plays into what they call the resolution of the image, or the finest details that you can actually see with that scope. So those things playing together gives you, this useful magnification. Generally speaking, it's really hard to actually get it to that, what they list as the maximum, because you kind of need perfect skies to really achieve that. The focal ratio is just it's sometimes referred to as the speed or the F ratio of the telescope. It's a representation of the ratio of the size of your focal length to your aperture, which helps you determine suitability of different types of targets. So this is kind of what I just talked about. So when you talk about the aperture and how the size makes a difference in the light you're gathering, if you have a 100 millimeter aperture scope and a 200 millimeter aperture scope, the 200 millimeter one is actually going to collect 4 times more light. That's the relationship you have with the volume of that circle that is the primary aperture. So the focal length, we talked about that. So yeah, the focal length, like I said, you get greater magnification. If you've got a longer focal length on the tube or a smaller focal length on your eyepiece, you're going to get a greater magnification. But with that greater magnification also comes a narrower field of view. So if you're looking to get something that's wide, like the Orion Nebula, you can't hammer it with a ton of magnification and expect to fit it all in your field of view of that eyepiece. So magnification, generally speaking, is how much larger your target's going to be versus when you see it with your naked eye. Mathematically, it's, like I said, the focal length of the scope divided by the eyepiece. We talked about the max useful magnification, the field of view. So we kind of covered that. So yeah, that F ratio is the focal length divided by the aperture. That's what gives you like 6.3 or 8 or that kind of thing relating to the picking your targets. So a higher focal ratio gives you more magnification with a narrower field of view. You can get finer details with that, but you reduce the brightness as a result. So now when you talk about eyepieces, there's two specs that you might see about eyepieces when you look online, because you can buy new eyepieces for your gear. We'll just address them real quick. I have an image after this that kind of shows what these are, but the exit pupil is the size of that projected focused image as it's leaving the eyepiece. For young people, they can get around a 7 millimeter opening in their eyeball, in their iris. But as you get older, that gets, less flexible like everything else. And older people kind of max out around 5 millimeters. So that's kind of the sweet spot for the exit pupil of an eyepiece that you might look for. The eye relief is basically how close or how far away from the eyepiece you can be or have to be to get to where the focused image is projected outside of that eyepiece. If you've got glasses, they usually suggest around 12 millimeters or so of eye relief. And there are special accessories for eyepieces and series of eyepieces that are made for people with glasses explicitly that you can get. They tend to cost a little bit more, but they do exist. And the shorter your focal length on the eyepiece, the shorter that eye relief tends to be. So if you get like a 3 millimeter eyepiece, you could practically have your eyeball on the eyepiece lens. Whereas if you've got like a 40 millimeter eyepiece, you're going to have much more eye relief. And just to kind of show the concept of that, you've got so this is the size of that projected cone of light coming out, and then the exit eye relief is the distance behind the eyepiece. So this is the eyepiece with the glass, and this is like the cup for the eyepiece, basically. Internet. Kind of neat, right? Because they cut it in half, the whole mechanics. No, I know there's something missing, right? Yeah. I'll write to them, tell them they could have done better. I wanted to see inside the retina. The other spec you might see, and this usually confuses a lot of people, is apparent field of view versus true field of view. The way that I've seen it written, the best kind of explanation of it is that the apparent field of view is the maximum area that the lens would show you if you didn't have any magnification involved. If you just looked through the eyepiece itself, how much of the sky would actually be coming in at you. Then the true field of view is actually that divided by the magnification, which is how much of the sky, when it's attached to the telescope, are you actually going to see. So it's not changing the magnification, it's just changing kind of how much area you're seeing around it. So you can see this moon shot here is the same magnification across the board with different field of view eyepieces. 40 on the left, all the way up to 82 on the right. And the kind of the wider your eyepiece field of view is, the more sort of immersive it tends to feel, because it tends to cover more out to your peripheral vision. And most people I won't say all, but most people tend to like that more kind of wide view for really feeling like they're inside the scope a bit. But as you get wider, it also gets more expensive. So for newbies starting out, eyepieces are kind of a secondary concern. The default ones, the stock ones that come with your scope will be decent enough, but you'll find over time that you can get nicer images and more interesting visual views with some nicer eyepieces. Yeah. Well, usually what happens is you use the stock ones and then you use a friend's, or you come to one of our parties and you use like a real nice eyepiece and you go, oh, it could be different. So yeah, but they can get expensive. Some of the eyepieces can be as expensive as a telescope. So, you don't make sure you kind of understand what you're buying before you go out and just plow money into it, because you could be buying redundant gear and that kind of thing. And there's plenty of other places to spend your money in astronomy. So there's no need to waste it unintentionally. So talk about the types of telescopes. This is just a rough drawing. Again, I just found this one on the internet, but we'll go through them a little more in depth. But there are multiple types of telescopes. Refractors use just lenses. Newtonian reflectors use just mirrors. The Cassegrain is actually just a mirror, but the Schmidt Cassegrain has a plate lens and mirrors, 2 mirrors, and the Maxitoff has a lens and 2, well, 1 mirror and 1 reflective surface that's essentially a mirror too. So we'll go into those a little more in depth here. Yeah, and there's a bunch of others that they start to get out of the price ranges and difficulty. Yeah, exactly. So for a newbie, these refractors are very simple to maintain and set up. The optics are entirely lenses. They're cemented into place, so unless you drop it, you really never have to do more than just kind of keep it clean and aim it and focus it. However, you do get less aperture for your dollar compared to reflectors that use mirrors, because lenses are more expensive to make. Each lens in the system has 2 surfaces that need to be polished and often coated, and the glass itself has to be internally defect-free as well. And the lenses also tend to make the overall scope heavier as a result as well. So where'd the mouse go? So there's some terms in here, let's see, that you might want to know. Some of these are kind of astrophotography specific terms, so it's good just to kind of know what they are, so you recognize if you're just doing visual, that doesn't apply to you, that you don't have to worry about it. But so the most basic refractors are known as achromatic, which means that they don't focus all the wavelengths of light to exactly the same point. They tend to be kind of a single lens to focus the image, and they only manage to focus 2 wavelengths of light at any one time. Well, yeah, 2 lenses, 1 in the back, yeah. one in front, 1 in the... 1 pack of lenses, I guess you'd say.
No, the front is always enough. You never get a single.
Okay, yeah. So, well, unless you're Galileo, right? But so that one doesn't correct all the way for the difference in how light moves through glass, right? It refracts through glass. So when you look at brighter objects like a planet, you'll see that the colors are still split apart on the edges of those bright targets. So that's and they also tend to suffer from a spherical aberration, where the target's only in focus in the center of field of view and not on the edges. Then you have apochromatic refractors, or APOs. They add additional lenses to correct different imperfections that are found in the achromatic scopes. They refer to it as a doublet, which is kind of why I didn't want to use that term, but it's more expensive doublet. Yeah, more expensive doublet that corrects one error, 1 chromatic aberration. Then there's triplets that add another lens to further improve the color correction, and there's quads that add a 4th lens that flatten the field of view as well, correcting for the spherical aberration. A doublet is usually kind of the sweet spot for visual astronomy, because anything beyond that is a little more than your eye is probably going to notice. So you don't, if you're just doing visual, you don't need to go splurge for a quad refractor. What's that? I disagree. You disagree? Well, for a newbie. Pretty much any aberration is visible to the eye or to the camera. Well, I don't know. I'll say that while the aberrations might be there, they tend to be much lesser, right? And so if you're keeping the target in the center, you don't necessarily care about spherical aberration, right? If you're talking full edge-to-edge field of view, yeah, well, then you need a quad. but most targets that people are looking at, well, anyways, so generally speaking, for a newbie, you're probably not going to start necessarily with a quad. They're a little more on the line of astrophotography side of things, but obviously you can find a fight online about anything. So if you want to go online and just tell somebody you think one thing's better than another, and you'll find a fight. But that, in my personal opinion, I think a double is kind of the sweet spot from the price perspective for the advantage you get out of it. So here's a general rough drawing. You've got the glass in the front held by what they call a cell. It's being focused down to the back. You've got a focuser that's moving the eyepiece in and out in what they call the draw tube. And then these baffles, which we didn't talk about yet, are basically just fins inside the tube that try to keep stray light from getting further down the tube and never getting the back, actually getting to your eyepiece. So you don't have stray light and you don't have weird other aberrations. And then the dew cap we didn't talk about either. Basically, if you had this, that's just like a hood over the front, kind of like you see on this DSLR. Yeah, or in the end there's a black one. Almost all the refractors have them, because if you just have the glass right at the front, stray light at very severe angles could still be entering the glass and cause all sorts of effects that you don't really want to be seeing. So this keeps it in a slightly darker spot. It also keeps the dew from settling onto that surface a little bit. Helps, yeah, not 100%, but it is a much better than not having it. So you'll tend to see those dew caps as well. So next one's reflectors, which are only mirrors. So there's usually at least 2 mirrors, not always, but usually 2. Well, yeah, usually 2 mirrors. The most common is called the Newtonian because it was developed by Isaac Newton, and it's kind of the earliest design of a mirrored scope. You can generally get them with a larger aperture, a longer focal length, less weight, and at a cheaper price compared to refractors. However, they can lose their alignment, so you do have to know how to collimate those mirrors to keep them aligned properly every now and then. And that's known as collimation. Watching reviews or tutorials online for how to collimate is usually a little bit scary for people the first time, because they feel like they could make it worse than they could make, when they're trying to make it better, but it's really not that difficult. You can master that pretty quickly, and it's usually just a minute or so or less of time to actually collimate before each viewing. It's also worth noting that the secondary mirror is an obstruction to the light that's coming to the front before it hits the primary mirror. So while it doesn't block your field of view, and it's not necessarily something you'll notice when you're observing, it does mean that you lose a little bit of light. So a refractor that's 6 inches with a 6-inch objective lens would actually pull in, I think it's like 20 to 30% more light than the reflector that has a 6-inch mirror. And if you look on the image here, you can kind of see it in the front. There's a little round thing that's got these spider veins that hold it in the center of the scope, and that's a secondary mirror. And we'll see here, that's this thing, the secondary mirror here. So this light that's coming through here, anything that's coming in the center area is being blocked from actually reaching the back of the scope. So that's that loss of light right there. But the light gets focused back onto that secondary mirror, which is usually just a flat mirror, and that kicks it out the side of the scope. So you actually view from the front of the scope, whereas a refractor, you're viewing from behind the scope. So if we look back here, the eyepiece is in the back end. So usually you'll have a 90-degree diagonal there, so that you can, like, kneeling down. Yeah, otherwise you have to kneel and get really far below the scope. When it's moving around, it's very uncomfortable. But with the reflector, you don't need a 90. The 90 is built into the design, and it's also at the front, so it tends to be a little, above the center line of your pivot points. Makes it a little more comfortable to view that way. And then the only thing that I kind of mentioned it but didn't explain it, was just spider, and that's just what holds that secondary mirror in place in the center. It's just little veins in the center, and that's what gives actually the diffraction pattern from those veins is what causes starbursts. If you're imaging with a reflector, you can tell because the images have a starburst pattern on them, whereas a refractor will not have the starburst. Now, a special type of reflector is sometimes referred to as a Dobsonian. It's actually just a Newtonian scope, but on a Dobsonian mount. So John Dobson created this type of mount to make it easier and more sturdy. So you don't have to put a large tube on top of a tripod. You don't need some beastly tripod to keep it from being blown around in the wind and vibrating from people walking around. These are very common. You'll see them all over the place. And the scope itself is identical to what we just looked at, the regular Newtonian. It's just how it's mounted, and then that base. So that's like a Lazy Susan base. So the only other difference is the mount. We'll talk about different mounts later, but this can only be an up, down, and pivot left and right kind of mount, which they call alt-as. But we'll talk about the other types later, which if you put it on a tripod, you could use the other type of mount. And the other type is a catadioptric, which is one that uses both lenses and mirrors. The most popular is referred to as an SCT or Schmidt-Cassegrain telescope, which is the design you see here. Basically, it's got a secondary mirror also, but instead of having those spider vanes, it's actually got a corrector plate. And the corrector plate, that glass is actually holding, there's a hole in the center of it, and this kind of pinches onto that glass and holds the secondary mirror up behind it. There's advantages to all of these designs, and one of the advantages with that is you can actually, for certain models of these, you can actually remove that secondary mirror and replace it with a whole different lens assembly and a camera, and it can really change the capabilities of your scope. That's very flexible like that. But and the other difference too is when you look at if we look back at these ones, in both this case and the refractor, the focuser moves in and out the straw tube with the eyepiece in it. But when you focus a catadioptric, it's actually moving the mirror, this primary mirror that's in the back, which I'll show you in a second. So it's actually completely moving the mirror, not just the eyepiece. The eyepiece stays stationary. But because the light comes out the back of the scope, like a refractor does, you'll see it have a 90-degree to make it easier to look through it without having to squat underneath the scope. So another fairly common version is a Maxitov Cassegrain. It's got a smaller blocking center part here, so you actually get more light in for the size compared to an SCT. Usually a narrower field of view and usually significantly more expensive. And I've never actually used one, but I've heard they're a little bit tougher to calibrate than the SCTs when you have to collimate them. So if you're going to pick a catadioptric, an SCT would be the way to go, but that's also a steeper learning curve than a refractor or a reflector anyways. So maybe not the best for your brand new first telescope. So here's the two designs of those two scopes I just mentioned. So here's that corrector plate and that insert that has the secondary mirror on it that I mentioned. Light comes past it. There's actually a donut-shaped mirror in the backside that reflects back into that secondary mirror. And then the secondary mirror narrows it down inside these baffles to the eyepiece in the back, or in most cases to the 90-degree diagonal and then the eyepiece. The Maxitov, you can see, has a markedly different front lens. And in addition to the fact that it's correcting differently because of this very concave shape versus the almost flat corrector plate on the Schmidt-Cassegrain, instead of having a hole in the center of it with a secondary mirror kind of screwed into it, it's actually got a anodized or aluminized secondary spot on the back of the glass. And that's what's reflecting back to the back of the scope. But it still has the donut-shaped primary in the back. There. So the other telescope, if you want to call it that, basically two telescopes connected together, is a binocular. These are good ways to start because a lot of people, for whatever reason, tend to have binoculars around already. I haven't really figured out why people buy binoculars but it just seems like everybody I know has one pair. There are binoculars that are designed for astronomy specifically with special coatings that are enhanced for the night viewing. You'll tend to see a couple different specs mentioned. One of them will be the prism type, one will be the glass of the prism, and then you'll see these numbers that represent the magnification in the aperture. So Portal prisms tend to be the prism of choice. They're designed by a guy by the same name. They tend to have a wider field of view and better light transmission, meaning they're losing less light when it's passing through those prisms.
Kind of become the more
Yeah, they've gotten a little better, yeah, but on the average still. And roof prisms are not called roof prisms because that's where they're mounted. They're actually the shape of kind of a roof, which when I first was looking at them, I assumed they were just mounted to the roof, and I was like, why does that matter? But then there's different kinds of glass. There's these back 4 glass and this BK7 glass. Everything I found online kind of said the back 4 glass is better, has better specs for it. And then they even broke it down to the fact that there's the European made back 4 glass, and then there's some Chinese kind of back 4 glass. And when compared, the European tended to have better transparencies as well. Probably not a super noticeable thing for most people, but if you've got the option and the prices aren't crazy different, then that's the way it would go. But the numbers, the 10 by 50, for example, are important to look at as well. The 10 is the magnification level of that scope of the binoculars, and the 50 is the size of the objective lens on the front of each of those sides of the binoculars. So the 10 by 50 means 10x magnification. You've got 50 millimeter objective lenses on it. So the bigger, just like with the aperture for a regular scope, the larger that is, the more light you're pulling in, the dimmer objects you can spot with it. The catch about the magnification is that if you go over a 10x, you tend to be in the heavy side of these scopes, or of the binoculars, and that tends to be heavier than most people can hold very steady. And once you get to that point, it becomes, it's really hard to focus on what you're trying to look at. It's less enjoyable to look at. So you almost have to involve a tripod, or sometimes a specialized mount on a tripod called a parallelogram. And now you've kind of taken the ease of binoculars away by introducing setup and additional weight and things to have to carry around with you. Not that those are bad things to have, as long as you know you're getting into it for that purpose. But if you want them to be something to just test and make sure that you've got the curiosity enough to go out frequently before you invest in something larger, binoculars are a good way to do it. And then there are what they call astronomy specific binoculars that have pro versions where they'll purge the inner cavities between the lenses with nitrogen, so it doesn't fog up. You don't have any moisture that gets in there when it gets cold, that kind of thing. So there are advantages to the pro versions. Yeah, so it's pretty good. Let's see. All right. So now there's also telescopes that are specific for astrophotography. So they're designed with the intention of using with a camera, and literally you can't look through them. So just so you understand what they look like again, you understand when you see it that that's not necessarily what you want if you're just looking to do observational astronomy. This catadioptric design, very similar to an SCT, except you can see that there's actually a camera mounted in the front here. This one, in this case, an actual DSLR camera. So this is SCT with that corrector plate, and where there would normally be the secondary mirror to send the light through the back of the scope, you remove that secondary mirror and they slap a camera in there, and there's literally no place you can put an eyepiece on this. It has a solid, not a donut shaped mirror in the back, so there's no light coming out the back of it right here, even though the focus knob's still back there. But if you'd have to put an eyepiece in the front, which means you'd have to block the light trying to get into your scope to try and look into the scope. So you literally cannot use a eyepiece with this style of scope. And then you've got the smart telescopes. We've got a couple of them over there so you can look at when we're done with the presentation here. These things range anywhere from a couple $100 to legitimately $100,000 for stupid reasons. Don't buy the $100,000. But this one here is something that literally just came out like in the last couple of weeks, and it's $100,000. And I can't imagine. I don't know. I can't imagine. No, yeah, I haven't quite figured out exactly how they think it's. Yeah, the web developer was expensive. Exactly. So most people, these are common. Dwarf 2 or Dwarf 3. They all look the same. These are C stars. This is a C star S50. This is a C star S30, and these are Vaonis Vespera 2, I believe, and a Unistellar Equinox 2. This is a Vaonis also called a Hyperion or something. That's the super expensive one. The concept of these is basically they're lightweight. They're pretty much, I think all of them have battery built into them. You can take them out, set them down, turn them on. They automatically look at the sky and figure out where they're pointing. They have GPS to figure out where they are in the world, and then they already know then how to find other things in the sky. So using your phone or your tablet, that's connected directly to that device wirelessly, you can just tell it, all right, I want to go look at this thing. I want to go look at this thing. The thing is, you're not looking at it with an eyepiece. You're telling it to start imaging that thing. So different nebulas or galaxies, whatever. And they all have built-in cameras in them. So it'll start imaging it and it starts to show up on your screen. It captures a bunch of frames in a row and stacks them on top with some math that causes it to increase the signal and reduce the noise in the image. And over time, you start to see the color and the details kind of develop on your screen. But there's no way to look through these with an eyepiece. So if you're looking for observational, those will not get you there. But they do have their own advantages. Like I said, being so lightweight, you can carry them with you if you're traveling. If you're in an area where it's hard to get good sky for much time, you can set these up and be imaging within a few minutes, and you can tear them back down and get back in the house within a few minutes. They can be good for people who are just kind of putting their feet in the water, trying to get used to astronomy, maybe learn about some of the stuff that's up there, but they're not necessarily going to be super great at teaching you how to find it by yourself, because it really does almost everything for you. If you're thinking about astrophotography, they're not a bad way to start either, just because the images that they take, you can take off of the scopes and you run them through post-processing later on a PC, which is all part of the traditional astrophotography. So it could be a quick way to gather the data, but give you the, flattens that learning curve a bit. But once you move from that to a real scope, because you want to get a larger aperture, you want to, image something that's much more faint or much smaller in the sky, you're going to eventually have to learn how to control the scope a little more manually yourself anyways. But at least this can help you figure out, do I have the passion for it versus just a curiosity? And they're only a couple $100 for most. These ones, these top three are very popular, and they're a couple $100. I think $550 for this one. Maybe it was a $350 or $400 for this one, I think. These ones are a little more expensive, and that one, don't touch. So now we'll talk about mounts. The mount, like I said, is the thing you're going to put on top of the tripod, and you put the telescope on top of the mount, and that helps you or enables you to articulate the telescope to point at whatever you need to point at in the sky. So there's a couple different kinds of mounts, but the general concept is you're going to have the tripod at the bottom. This here is the mount in this case. You see how it's got different axes for rotation. And then if you've got a refractor or a Newtonian like this, they often have these rings, these tube rings that clamp onto the OTA itself. And then at the bottom, you'll have a bar that's connected to those rings that you clamp onto the mount. And that's how it holds the telescope in place and then allows it to attach to the mount. This particular type of mount is called an equatorial mount. You can see how all the weight's hanging off the back side of this. So you'll often have a counterweight on the other side because you want it to be perfectly or as close to perfectly balanced as you can on the mount for it to not have torques and unevenness. It's a lot easier to keep focus and all that or to keep your tracking and all that kind of stuff smooth if it's on balance. The other stuff we kind of talked about. Oh, and then these slow motion knobs are important too. If you're going to get a mount like this, you don't want the kind of mount like a camcorder mount. We'll go over these in a second. If you get the ones that you have to just tighten the knob and it just squeezes against the mount, it almost always shifts you a few thousand light years to the side. Once you get it where you want it and you tighten it and it goes. These slow motion knobs allow you to make very micro movements so that you can track objects through the sky. You get it into your field of view. You don't have to lock it down, and you track those objects slowly through the sky much more easily. So it's a much happier experience. But let's go through a couple types here. So you've got these alt-az mounts or altitude azimuth mounts. Sometimes a version is a pan tilt, which is like a camcorder, and another version is a fork. What that essentially means is the only way they can move is up, down, or left and right. Those are the axes that it can move in. Generally, not a problem if you're just doing visual. If you're doing astrophotography, it's a problem because it can't rotate with the object as it rotates through the sky. That'll smear it on your sensor, your camera sensor. But you can see here, this one it's just up, down, left, right also, but it has the micro movement knob, so you don't have to worry about jerky movement while you're targeting something light years away. The Dobsonians or parallelogram, the Dobsonians, we talked about those before. This is also an alt-as mount, only moves up and down or pivots left and right. This is another version of a Dobsonian mount, essentially. And this is a parallelogram I mentioned briefly with the binoculars. You can kind of see them shadowed up here. If you just put binoculars on top of your tripod, you can't look at zenith, which is straight above you, and you can't look very steep because the more you tilt that upward, you're kind of shoves your face into the tripod, right? So this parallelogram offsets it, and then it's got counterweights because you've got weight over here, so you have to have counterweight over here so the tripod doesn't tip over and everything stays balanced. But these two arms of the parallelogram, as you move up and down, stay parallel to each other, hence the name. And they actually make it so that if you were to take this and be pointing at something and you just dropped it straight down, didn't pivot it at all, it should still be pointing at the same thing if you hand it to somebody shorter than you, which is kind of nice. But you can see how it moves you away from the center of the tripod and gives you a lot of clearance, so you can look at zenith and you can look at much deeper things in the sky. But that adds weight. It does add setup. So, may not be. That's why if you get these large scopes or large binoculars, you're adding additional gear almost indefinitely. So now you've got German or Chinese equatorial mounts. You'll see them called GEM or SEM. They're the exact same concept in terms of how they work. You point them at the North Pole, and the mount will rotate with basically against the Earth at the same speed as the Earth, so that whatever you're pointing at, you're also going to rotate with it at the exact same speed. So that allows you to keep a target in your field of view for well, essentially indefinitely, as long as you want, depending on how perfectly you polar aligned and how perfectly your clock timer is for that motion in the mount. The only difference between the Chinese version and the German version, the Chinese version, you can see here, kind of brings the weight a little bit in closer to being above the tripod. So you can get away with a smaller amount of counterweight. It's supposed to use less power. So power is always something when you're out in the field. If you don't have a wall socket with you, power can be limited. So sometimes that's nice to have a lighter burn on your power source. But otherwise, the movement's identical. The concept is pretty much identical. And then because it's more centered too, you can actually put more weight on them. You could have a bigger telescope on a slightly smaller mount compared to a German equatorial version. But the German equatorial are more common. I've got a wedge mount. So if you I've actually got one over here and I'll set up. If you take a fork mount, which is only up, down, left, right, and you put it on a wedge so that the wedge is in the right same direction as the wedge is polar aligned, then when this rotates, it's going to be rotating around the pole. So that can be the one that's tracing or counteracting the rotation of the Earth. And then this pivot point here allows you to point anywhere else in the sky. So you can turn an alt-as mounted fork mount like this into something that technically is polar aligned and like similar to a German equatorial. Now you'll hear the terms push to and go to. Push to means you've got sensors on each of your axes, but no motors, basically. So with a push to controller, it'll show you how far away. You have to do a little bit of alignment up front so it knows where it's starting out, what it's pointing at to start out with. But then you can tell it, like, I want to go to this particular target. It tells you where to push the telescope, how far over. And as you move it over, you'll see the numbers count down and then how far up to go or down to go. So it allows you to push to a target. The go-tos are motorized versions of that. So you have to do your polar alignment first so it knows where it's at, where it's starting out, and it knows how good or bad your polar alignment is, and it corrects for that. And then when you tell, say you want to go to a specific galaxy or something, it moves there on its own. Okay, and then the last one here is trackers. So if you just have a DSLR camera and you want to start out with that for astrophotography or something like that, you can get these small tracking mounts. They only, you polar align them, but they only rotate in one direction. So you put like a ball mount on top of it. That gives you the freedom to point in any direction that you want. But this flat surface behind it would be polar aligned to the pole. So where this attaches right behind it is actually going to rotate like a record player, essentially. And that's what's taking care of counteracting the rotation of the Earth so that you can focus on a target for a long period of time and track it as it goes through the sky. There's different combinations of things. This is a small scope with a DSLR on one side that works because they're balanced with the weight, that kind of thing. So you can do a lot with a tracker, and they tend to be portable enough where you could bring them with you technically. If you were going to be doing astrophotography, it's not a bad way to start because they're not that expensive, and you can fit them in a bag. So that's the rotation pattern. So if you still aren't necessarily sure how dedicated you are to the hobby yet, then I would consider, like I said, starting with binoculars or a smart telescope. For planetary viewing and the moon or double stars, I'd go with at least a 70 to a 90 millimeter refractor. If you just have a general one of kind of looking at everything, whether it be comets, nebulas, galaxies, the reflectors kind of tend to be the best bang for that. Look for something that's at least 130 millimeters and under an f8 for the speed. It's kind of in the middle of things, sort of a jack of all trades sort of range. Catadoptrics, like I said, they're a little more complex to manage in terms of collimating them and that kind of thing, and they're a little more on the expensive side, so they have a slightly steeper learning curve, but they're very flexible. You can grow with one of those for quite a while because you can run them in different modes. Like I said, you can take off that secondary mirror and put a whole other lens assembly there, and that changes the scope. So if you're willing to take on a steeper learning curve or you feel confident about it, they're not a bad choice, but they're not the easiest ones to start out with. And then above all else, the best scope that you can get is the one that you're going to use. Like I said, if it's too heavy, it's too big, if it's too complicated, you're never going to take it outside. And what you really need to learn these, how to do this kind of stuff is really just practice and just doing it over again a couple times, and do it with people like us that can help you get past the friction points that seem like they're stumping you. But like it says, you don't want to buy an expensive 14-inch 200-pound clothes rack for your living room. So you can check out this website if you want. There's some of the light images I took from here, the light path images. There's a lot of good information on this guy's website about different scope designs and minimum sizes and expectations. And this will be up on YouTube as well later. So if you want to come back and pause on these slides to get the URLs, you'll be able to do that. For mount selection, again, that fine grain slow motion control, definitely kind of mandatory, makes your life easier. Alt-Az mounts are quick and easy to set up, easy to point to a target in the sky because it's a very natural thing to kind of think of up, down, left, right when you're moving manually. But the equatorial mounts, they do require polar alignment, and those are going to be better if you think you might get into astrophotography at all. And it's an awkward movement to move in that orientation if you're trying to manually do it. So you're more required in a way to make sure you polar align those before you start looking with them. But once you do, it's very easy to use them with the go-to functions. Almost all the German equatorials, most of them tend to have go-to once you get up to those decent sizes. So another hint is just join an astronomy group. You're going to learn way more when you feel less like everything is less daunting, and when you don't go out and burn an entire night and without making any progress on fixing whatever is preventing you from getting further in the hobby. We do around 12 public events a year, all year round, around the new moons. We do an additional 12 or so outreach events with other groups. You can tag along with us as a volunteer helper. You don't have to be somebody that mans your own scope, and you can learn from us on the fly just by observing and watching what we do and what we tell everybody else and how we set everything up. And we also do private and impromptu events with the group. We'll do, a random midweek. If we, like today, it was a very nice sky out there. Might have been a day when we would have thought to go up to the lake, not an announced event, just something we would mention on Slack and see if anybody wanted to show up and, meet and take advantage of the fact that good nights don't always come on a Friday, right? But yeah, you can just learn and problem solve way faster by just kind of being surrounded by it. Plus it lowers that barrier of like, when do I want to go? Because there's events already planned, and there's already going to be people that are going there. So it's like, you're not just going there by yourself. You're not just going out on your own. So if you are in this Mid-Hudson Valley area, including the west side of the river, you can join our group if you like. And any questions? Dave?
Steve, you may want to point out that they can come to our events, no cost.
Oh, yeah. Yep.
And get their feet wet, and then if they really become a member, support the club.
Absolutely. Yeah. All of those public events that we do, the 12 a year before the new moons, those are open to the public. They don't cost anything. You don't have to be a paying member to show up to those. Happy to let you look through our scopes that we set up when we do those, no problem. So you can get your feet wet with what other scopes, how they behave, what they can do, and you know, as well as learning lots of things. And then if you find it useful and you really want to, you know, find you've got a little more of a passion for it, you can become a paying member. There's other benefits to that. You can borrow other gear. We have refractors and reflectors and stuff like that that you can borrow. We have cameras you can borrow if you want to try and dip your toe into these different areas of the field without buying anything up front. And the membership's $25 a year, so it's, you know, pretty affordable in the long run either way. But there's a lot you can do with that without having to then spend a couple $100s before you know what you're doing.
Let's have a presence on Facebook groups.
We do have a Facebook group. We post our. Oh yeah, sorry, the page. Yeah. So what we have for social media set up, we have a Facebook page. We kind of just post our upcoming events on there, and occasionally some random Facebook other, you know, space related posts get on there as well. But we have Instagram. We don't utilize that to the level we should, but we just don't have time for it. That's why part of one of the things we want to do is to get a social media person to really kind of dedicate to that. We have YouTube videos. We post our recordings from these events onto YouTube, and we have Slack for real-time chat within our group. So if you're a paid member, then you can be part of the Slack environment, and that's where we kind of do those impromptu organizations. But we share images and you know, all that kind of stuff all day long. So
We could be pumping out a lot of images.
And Groups IO.
yeah, we have Groups IO as well. Groups IO is kind of open to the public, and also our membership. It's mostly used for just announcements generally, and the newsletter, just an email thing. Yeah. So yeah, we have a lot of imagers. We got 15 or so, probably at least, imagers in the group. So there's a lot of good pictures that come out each month.
And of course, Meetup.
Yep. Yeah, and then meet up for organizing the events themselves. Yeah. Yep. Celeste. Hey.
Telescope/hobby question.
Yep.
So I've been wildly dabbling for about 3 years now.
Great.
But speak to maybe, I always think of the negative, I don't know why, but can you speak maybe to some of the pitfalls that maybe someone new to the hobby might fall into that advice, don't do that, or save your money elsewhere? You gave a couple suggestions on the slide.
Sure.
Love to hear more about it.
I think the biggest thing I see people do. So he asked about are there other pitfalls for new people to the hobby, because he's been in it for a couple of years now. But you know, is there anything that I would suggest avoiding to save money and not waste money? Yeah. So what I see quite often, like an accessory fever. A lot of us like toys, and getting that new toy is always fun. And you think that you can buy your way out of whatever your problem was. You're like, oh, I can't seem to get that to work. I probably need this adapter, or I need this, you know, maybe if I had a better camera, then I could see through that telescope better and image better. But a lot of times it's not the gear, it's the user. You just need more skill. Yeah. Yeah, go ahead.
So I got my first telescope in 2022. So I'm close enough to it, but I had a 9.25 inch SCT.
Oh, yep.
And that was a huge mistake.
If you buy too big too fast, you have to be even more precise when you're setting it up. And if you don't know what you're doing yet, that's a steeper curve.
I got it to work, but it was just about the hardest thing I've done in my life. And it took 3 months before I could do stuff proficiently.
Yeah, that's a good point. I know I've got a friend that has a 9.25 also, and and he was thinking, he's always looking at the 11 inches, right? 11 inch SCTs and thinking, oh, maybe I need that. I'm like, you've got a lot to learn yet on the 9.25, and that's not the easiest one to learn on either. So yeah, don't go out there and buy the behemoth, not only because it's hard to move around, but because it is that much more sensitive.
But there's also the tendency to do the opposite and to buy a cheap scope and well, you know, I'll try it and, you know, see if I develop an interest, based on the scope. And often the problem is when you buy a cheap scope, the quality of the optics are hit or miss, but usually it's the mount that's really poor.
Yeah,
and
so
you get frustrated trying to find anything or to stay pointed at it, and you pay $200 and might have a decent piece of glass in it, but it's not going to have a good mount.
Yeah, one of the things about this hobby is it has everything, because it's got toys all the way up to full on, leading edge research level hardware. You can buy everything in between, and so if you buy a toy, you kind of get what you pay for, as long as, especially on the new market. I got you.
Yeah. The other thing I would say.
Hold on, did I unmute that for you? There you go.
The other thing I'd say, if you're completely new to the hobby or relatively new to the hobby, don't fall for the marketing hype. You'll see things, this, 400 magnification. Well, from what Steve
better be
said,
this big.
that's useless.
Yeah.
Yes, theoretically you can do that, but you won't see anything because there's a limit. There's a thing called the Dawes limit, which will tell you the smallest thing you can see with that scope. So it doesn't matter. So don't fall. And the other thing is look at reviews. Like if you're looking at scopes in that, if you're, I kind of like the scope, look for reviews. There's discussion forum. What's the
Cloudy Nights has a lot of good discussions, and what's the other one?
Night Sky or
Night Sky.
Cloudy Nights.
Yeah, Cloudy Nights is the main one.
Yeah.
Yeah.
Cloudy Nights, and look at reviews and what other people are thinking of that. You can learn a lot.
Yeah, because people that actually know what they're doing will have gone through and really torn them down to see what they can do performance wise, and they'll.
So don't be afraid to ask questions.
And don't be afraid of used stuff.
Yep.
Here's the economics.
Yep.
Buy $150 department store telescope. You're going to sell it for $10 at a garage sale. Spend $300 for a used 8-inch Dobsonian telescope like we have in our thing. You'll be able to sell it for $300.
Yeah, physics are physics. So good glass is good glass.
Your risk will be a lot less.
Yeah.
So if you have other people in the club to help you advise, I mean, astronomers generally take good care of their equipment. So used stuff is usually a pretty good buy.
Yep. Do exercise the normal caution you would for buying anything online. There are still some people that are scamming people on those sites, but you can, a lot of times doing it in person is a good way to make sure that doesn't happen if you can. Some people won't sell unless they can.
And you can always
drop it
borrow
off.
scopes from the club here.
Yep, they can always
That's what I
start.
was just going to say.
Yep.
We have lots of scopes to borrow for a couple of months and try them out. Actually longer because it's cloudy. And then there's every year there's what would we call it? A conference?
NEAF.
Meeting in the Northeast
Astronomy Forum.
Astronomy Forum down at
Rockland
Community College. It's sponsored by the club that's south of here, but the Rockland Astronomy Club, RAC.
Yep.
And there's all these vendors and there's talks and things, and so you can just wander around and talk to people and look for stuff and do that. So
yeah, usually you'll see us bumming around there too. Yeah.
So we'll go there.
Yep. You got another question?
Yeah. So this scope, I think, I know it was a gift. I got this scope as a gift. I believe it's $150 department store scope.
Okay.
Just kind of a gift from a family member, just because they knew I had an interest.
Sure.
And I believe it is based on your presentation. I could be wrong, obviously. I think it might be a refractor with an equatorial mount.
Okay.
Possibly.
Yeah, we'll find out.
Yeah. I think, if I had to guess, maybe. But my primary interest is actually in observing galaxies.
Okay.
And so that's something I'd like to build up to. In terms of, somebody who's very new to the hobby, what would you recommend, for someone like me as an investment in a scope that might be able to do that at an entry level?
I mean, the one you got is always a good place to start, and we can always push it to its limit, right? And see what it can do. The nice thing about galaxies is there's quite a range of sizes up there. Andromeda, for example, is like 5 full moon widths. It's probably too much magnification to get all of Andromeda in it, possibly, right? So Then there's other ones that are super tiny. So just because it's a smaller scope doesn't mean you won't be able to see galaxies still necessarily. But
yeah, it's what's important is for galaxies is dark sky. And
yeah, because they tend to be kind of faint.
If you don't live in a dark sky area, you are going to want to travel, be able to travel. So have a scope that's portable, that's big enough to see. But even a Texas Star Party with a 70 millimeter, a 76, TV 76, you could see, like you look at the what's the group in Virgo? Anyway, you can see dozens of galaxies in one view.
Oh, like Mercury
in a small scope
yeah.
because you have good contrast.
Yeah,
and that's the key.
Yep. Yeah, if you got light pollution, that's going to block out most of it.
Which is why we go to Lake DeConnick State Park for our monthly
Right.
Star Party schlep, but good dark skies from around here. Better than what we've got.
Yeah.
Anywhere nearer,
but still nowhere near.
Oh yeah, it can get way darker than that, but yeah, the Adirondacks has really good dark skies. Also, if you're ever in that area.
We identified a bunch of dark.
Yep. Pitch.
If you go on our website, there are under resources, I believe, from the resources menu, we've identified a bunch of places you can go with dark sites that you can get on. It's legal to go on, and one of the issues is there are a lot of parks and things, but they all close at sundown. So that
who's actually going to let you be there, basically.
Yeah, but the ones that are identified, you can use.
It's like a printable single page thing that he put together for each of these sites, and it kind of talks about what you need to do to be there. If you have to talk to anybody to sign up for anything, or sometimes you got to pay a fee to be there at night or whatever, that kind of thing.
If it's on a campground.
If it's on a campground or something.
I actually have been to about 4 or 5 of the Star Parties at kind of State Park, and I've actually spoken with Jack a bunch of times.
Okay.
Yeah,
we don't recognize faces. Yeah. Yeah. I hardly know these people. Yep. Yeah.
Probably over the last 5 years, I've been going occasionally when I can, so I really appreciate it. Cool.
Good.
Do you recognize me now?
Yeah, exactly. Yeah, if you close your eyes, I'll know who you are. Yeah. Yep.
Well, we should look at his scope.
Yeah. Okay. So yeah, let's break down. Did you have any questions in the back? Okay. Sorry. So we're gonna break down and have the scopes that are around the room and kind of talk in person.
I've lost host because I turned my phone on.
Where would be a good place to put it?
You could right there is fine. Yep. Okay. And then I don't know.
So,
Jack's got a movable camera, so I think he's gonna. Oh yeah. Sorry. Let me unchair.